Okay, 9.3, answering questions about the mean of a population. So let's start with a review of what a sampling distribution is. Those were the distributions we were looking at in the last two sections, and they had sample means on the horizontal axes for all possible values of x bar on the horizontal axes. So we're going to start with a quick review of what those sampling distributions are. So keep in mind it's the probability distribution for a statistic, and we're interested in x bar in this chapter. 2, it shows all of the possible values of the statistic on the horizontal axes. It gives you the probability of each possible statistic. That tells us how often we can expect to see particular values of your estimator in your estimator's x bar. And it's not really going to do particular values or specific values, but ranges of values. So for instance, what's the chance you get an x bar greater than something, or less than something, or between two values? All right, next it gives us important characteristics of the estimator, such as bias and precision. So remember, bias is talking about center, and precision is referring to spread. It's going to allow you to quantify how far off our estimates are likely to be by calculating the probability that an estimate falls a specified distance from the population value. And last, it's used for making inferences about a population. It allows you to generalize the results of a survey, which comes from your sample, to a larger group, which is the population. Let's start with an example. So let's imagine a large population, such as all iPad batteries in the US. Let's assume that these iPads have a 10-hour battery life, give or take 3 hours. Suppose we take a simple random sample of 25 iPads and calculate the average battery life. So notice that we have 3 things in here. We have mu, the mean for the population. We have sigma, which is the standard deviation for the population. And we also have our sample size. Okay. So the question is, can we use the central limit theorem to create the sampling distribution for x bar, which is the average battery life for a random sample of 25 iPads? So just like earlier, we've got to check those 3 conditions for the central limit theorem. First one, which deals with center. In other words, if condition 1 is met, we know the center of this sampling distribution. So that the sample is collected randomly from the population and observations are independent of each other. Sample can be collected with or without replacement. So we are doing random samples, and it is safe to assume that the battery life of one iPad in our sample has no effect on how long the battery lasts on another iPad in our sample. Condition number 2, remember, is what allows us to predict the shape if it's met. This is the one about sample size. Sample size n has to be large enough unless the population is normally distributed. So we can check that off because we're using samples of size 25, and the rule says they have to be at least a sample size of 25. Your population has to be normal. And condition number 3 is the one that allows us to predict how spread out these values of x bar are going to be, or what their standard error is. So if the sample is collected without replacement, then the population size, capital N, must be at least 10 times bigger than the sample size, lowercase n. And since we're dealing with a sample size of 25, 10 times 25 is 250, and it's safe to assume, most likely, that there are more than 250 iPads out there. All right, since these 3 conditions have been met, we can use the central limit theorem to create the sampling distribution for x bar. So we're going to do that below. Notice this is just what we were doing in the previous section, so it's really just a review. We know that this distribution is going to be normal. It's going to be centered at our mean, which was, let's see, 10. And it's going to have a standard error of 3 over the square root of 25, because 25 is our sample size. So that's going to be normal, centered at 10, and a standard error of 0.6. And again, you might want to press pause and double check that you know where that 0.6 came from. We had a population mean of 10 hours, population standard deviation of 3 hours, and a sample size of 25 iPads. All right, so our horizontal axis is labeled as sample means, or you could say the mean battery length of a sample of 25 iPads. The most important thing is to remember that these are talking about groups of iPads, not individual iPads. And their mean battery life is centered at 10, the population mean of 10. And we can use that standard error to put a few more numbers on our axes. So we're going to add 1, 2, and 3 standard errors to either side. And that gives us an idea of what our sample means will look like. So according to our empirical rule, we shouldn't really expect a sample mean less than 8.2 or a sample mean greater than 11.8. Okay, so on the next page, according to the sampling distribution, what should we expect the average battery life of our sample to be, give or take how many hours? Well, we expect our average battery life for our sample to be 10 hours. It's the most likely outcome. Give or take, and here you may have a difference of opinion, but you could use one standard error, which is 0.6 hours. Or if you want to be more sure, you might argue that you'd rather use 10 hours plus or minus 1.2 hours. This you'd be a little bit more confident because you're using more standard errors. So note that this is 2 standard errors. And that's what we started looking at in chapter 7 with confidence intervals. If you wanted to be more confident, you had to use more standard errors. And so here a conclusion that we should expect our sample mean to be 10 hours, give or take. Let's go with the 1.2 hours so you can be more confident. That conclusion is useful because it implies that in general, we can predict where X bar will fall relative to mu. We can predict where our sample mean will fall relative to the population mean. Okay. In fact, what's the probability that we get a sample mean that falls within 2 standard errors of the population mean mu? Well, remember from your empirical rule that approximately 95% of the time we should get a result within 2 standard deviations, or in this case 2 standard errors, of the center of the distribution, or the population mean. In fact, if we look at our distribution from the previous page, we'll find that 8.8, oops, looks like I went the wrong way. Let's go back. Here we go. Got 8.8 and 11.2. There's our 2 standard errors right in the center. That should include 95% of those sample means. So again, the probability that we get a sample mean, X bar, in between 8.8 and 11.2 hours, that's 95% of the time. So that indicates that X bar is very likely to fall within 2 standard errors of the true value of mu. And very likely because it happens so often. And that is true as long as the sample size is large enough. If we have a small standard error, then we know that X bar is quite likely to fall close to mu. All right, and here's a big idea, similar to what we saw in chapter 7. If we can predict that X bar will fall close to mu, the population mean, then we can also predict that the population mean mu will be close to our sample mean, X bar. It's very similar to me saying that I'm standing 3 feet away from the board. And that means that the board is 3 feet away from me. Not really anything different here with this big idea. Again, if we're saying that X bar is close to mu, then we can turn that around and say mu should be close to X bar. Whatever sample mean we get, it should be very close to mu. Mu should be very close to our sample mean. Okay, so number 3, let's return to our example. Researcher takes one random sample of 25 iPad batteries from the above population, finds that the mean battery life is X bar equal to 9 hours, and the sample standard deviation is S equal to 3 hours. The researcher then reports a confidence interval of 9 hours, give or take 1.2 hours. In other words, the researcher is confident that the true mean battery life of the population of iPads is between 7.8 hours and 10.2 hours. This confidence interval could also be reported in the following forms. So they can say 9 plus or minus 1.2 hours, or actually give the endpoints of that interval. Before we go any further, just a quick reminder, if you take 3 and divide it by the square root of the sample size, you get 0.6. And if we double that or use 2 standard errors, that's where this 1.2 comes from. So they're using 2 standard errors for their confidence interval. confidence intervals report the sample mean, x bar, plus or minus some amount. This some amount is called the margin of error, just like chapter 7, which tells us how far from the population value our estimate is likely to be. So remember in chapter 7, we did p hat plus or minus a margin of error. P hat was the proportion of our sample that had a characteristic that we were interested in. Chapter 9, we're going to use the same format, except our statistic is a mean. We're going to add and subtract the margin of error from that. Okay. These confidence intervals provide two pieces of information. They give you a range of plausible values for your population parameter, mu. Plausible means it would make sense that it's something in there. It wouldn't be surprising. And 2, the confidence level, which expresses our level of confidence in this interval. So they're calculated as follows. So x bar plus or minus that margin of error, like we mentioned here. And keep in mind that a margin of error is just a couple of standard errors. And how many standard errors you use is going to affect the width of your interval. Right? The more confident you want to be, the more standard errors you're going to use. All right, so let's consider what is meant by a range of plausible values for our population parameter mu. By taking another look at our simple random sample of 25 iPad batteries, the mean battery life of 9 hours, so we've got x bar equal to 9, and a sample standard deviation of 3 hours, s equal to 3. Reminder, in this case, we have access to the sample data, and we were able to calculate the sample mean, x bar equal to 9 hours, the sample standard deviation, s equal to 3 hours, and that also gives us the estimated standard error, which again is 3 over the square root of 25, or 0.6 hours. Okay. So the question then is, which of the following sampling distributions for x bar, the mean battery life of a sample of 25 iPads, could have produced that sample mean x bar value of 9 hours? So there are 9 possibilities here. First one is assuming that the population mean is 7 hours and that the population standard deviation is 3 hours. And 3 over the square root of 25 is where that 0.6 comes from. So it's a what if. What if mu was 7 hours and sigma was 3 hours? Would it be plausible that we get a sample mean of 9? Right? Most of us would say probably not. So we would rule out a population mean of 7 hours because it's too far away from our sample mean. Right? And if we go through all 9 of these, and I encourage you to press pause and take a look at them, the question's really the same. What if the population mean were 7.5 hours? And always assume sigma is 3 for this particular exercise, which is what's giving us those standard errors. StatCrunch just refers to it as standard deviation. So you can cross that out and put standard error if you prefer. Right? And the question again is, if you got a sample mean of 9, could it have come from that distribution? Well, if the population mean is 7.5 hours, a sample mean of 9 hours is in the distribution, but it's beyond 2 standard errors. So many of you are going to think, all right, that's a little too far away. I may rule this one out. And others may think, nope, that's within 3 standard errors. I'm okay with that. So we'll put a question mark here. And in this one, we'd have to say yes or no based on how confident we want to be. Right? But the third one, mean equal to 8 hours, notice that a sample mean of 9 hours is within 2 standard errors of the center. So most of us would say, yes, this is something we would consider. Population mean of 8 would be entirely plausible if we got a sample mean of 9. In other words, it's close enough to our sample mean that it would be a possible value or plausible value of mu. And if you look more closely, you're probably going to agree that all 3 of these in the middle are also possibilities, because our sample mean of 9, that's probably a little too far over, is right near the center. They're all within 1 standard error, so any one of these population means should be on our list of possibilities, which means it should be in our confidence interval. Down here, same thing. 9, somewhere in the middle. It's within 2 standard errors, so we should include this as a possibility. This one's where you're going to have a little bit of a disagreement. Some of you may agree that's close enough. Others may feel that it's too far away, so we'll put a question mark on that one. And here all of us should agree that that's too far away. A population mean of 11 hours probably wouldn't lead to a sample result of 9 hours. So we'd probably take this out of consideration. Right? So are these the only sampling distributions that our X-bar could have come from? The answer is no. Right? Any mu or any population mean between them would also work. So between, let's say, 7.8 and 10.2, those were the values we got from the previous page, would also work. And that means things like 7.9, 7.95, 10.05, any number in between those also work, even though I don't have a picture to go along with them above. Okay, down at the bottom of the page, a confidence interval provides a range of plausible values. Again, plausible means it makes sense, seems realistic. It's a range of plausible values for our population parameter mu. This means that all of the values in the interval, not just the endpoints, are plausible values for mu. It also means that our sample result X bar is a plausible result given a sampling distribution for any value of the population mean mu within our confidence interval. In other words, if mu was any number in between here and here, and we drew a sampling distribution to go with it, our sample result of 9 hours would be somewhere close enough to the middle that we would think it would happen, often enough for us to say that's a reasonable value for mu. All right, let's take a look at what the confidence level means. The following is the normal model for the sampling distribution for X bar. The mean battery life for a random sample of 25 iPad batteries. And this was, again, when the population mean was 10 hours. Population standard deviation was 3 hours. So remember that the standard error came from taking 3 over the square root of 25, which is where we got our 0.6. So you look more closely at your horizontal axes here. These are all possible values of sample means, or X bars. And we got these by adding 0.6 to the previous value. So 0.6 plus 10 gives us 10.6. If we subtract the standard error, 2 standard errors, or 3 standard errors, get those numbers on the left. All right, so what we're going to do is take a look at 2 situations. The first one, a student decides to take a random sample of 25 iPads and finds a sample mean X bar equal to 10.8 hours. So they got their sample mean right here. This student then calculates a confidence interval using 2 standard errors. Will this interval capture mu? We're going to assume that their sample standard deviation was also 3 hours. So it gives us standard error equal to 0.6. Right? So if we take their sample mean, plus or minus 2 of these standard errors, gives us a confidence interval from 9.6 up to 12. And you may want to press pause and double check those numbers. Visually, it means their interval goes from about here, 9.6, up to about here, 12. And so they're saying any number from that left endpoint all the way up to that right endpoint and including it are possible values of mu. So what we would see is that this is a successful interval. It does include mu equal to 10. Okay. So it's a successful interval because it includes the population mean. All right, student number 2, another student, decides to take a random sample of 25 iPads as well, but finds an X bar of 8.3 hours. So they're right about here. Okay. They also calculate a confidence interval using 2 standard errors. And the question is, will this interval capture mu? So we're still going to assume that the sample standard deviation is 3. It's a big assumption, but just to make this a little bit easier for us, which means they also have a standard error of 0.6. Okay. And in this case, actually I can change that. Remember the population standard deviation was sigma. We can assume that they knew that going into it. Okay. So in this case, they take their their sample mean, add and subtract 2 standard errors, and they come up with the confidence interval that goes from 7.1 up to and including 9.5. So again, press pause, double check those numbers. If you come up here and draw those in, 9.5 is roughly there. 7.1 is roughly here. So they would be saying any number in between those two and including those endpoints are possible values of mu. Now the bad news for this student, notice, is that they didn't capture mu. 10, mu equal to 10, is not in their interval. Doesn't mean they did anything wrong. It just means they were one of the unlucky folks. They got a sample mean so extreme that it was too far away for 2 standard errors to give a confidence interval that's successful. So the question then becomes, how often does that happen? So that's our next piece here. What proportion of the X-bars in our sampling distribution will produce a successful confidence interval using 2 standard errors? Successful means it includes mu in it. Okay. And then the other question is, what proportion won't work? So let's look at the successful ones over here. Right, if we were going to use 2 standard errors, they got a sample mean of 10, that would work. Our confidence interval will go from there to there. If they got 10.6, well, that would work too. Their interval will go from there to there. And some of you may already know that if their sample mean was right here, that would also work. I can't draw this one quite far enough over. It's getting in the way of the next one. But here's our cutoff. If we go any further to the right, if our sample mean is any bigger than 11.2, it's suddenly too far away for this procedure to work. And for similar reasons, if we go down 2 standard errors to the left, here's our cutoff down here. Anything below that isn't going to work. It's going to be too far away. So we're interested in all these sample means in the middle. So it turns out 95% of them will work. So 95% of the sample means will produce a successful interval, which means they produce an interval that includes 10 or 10 hours. Right, that's good news. That happens a lot. 95% of the time is a lot of the time. Right? The bad news, obviously, is that there's still some that aren't going to work. So if you're beyond 2 standard errors and you do this procedure, then this remaining 5% are going to have, it's not 50, but 5. Confidence intervals that are not successful. So 5% of the sample means will not produce successful intervals. But the good news here is that there's a lot more sample means that give you successful intervals than there are that don't. So that's where our idea of confidence comes from. Because this happens more often, we're more confident, or we're confident we get one of those than getting one of these that don't work. Right? Those don't happen very often. All right, so one more note here. A confidence interval that uses about 2 standard errors, so X bar or sample mean plus or minus 2 standard errors, has a 95% confidence level and is referred to as a 95% confidence interval. You're going to find that there's a more exact value to use here, just like in chapter 7. We're going to find it depends on your sample size. Okay, so number 6, the confidence level tells us how often the estimation method is successful. Our method is to take a random sample, so just one random sample, calculate one X bar, one sample mean, and then calculate a confidence interval to estimate the population mean. If the method has a 100% confidence level, then the method will always work. And that means your confidence interval is going to be incredibly wide. It has to incorporate every single number that's possible. So if you're talking about heights, mean heights, you probably have to start with 0 and go all the way up to, well, it depends on your subject. If you're talking about people, 8 feet, 9 feet, you're talking about intervals that are too wide that really aren't going to be of use to you. So we don't tend to use those 100% confidence levels. If the method has a 95% confidence level, then the method works 95% of the time or for 95% of the sample proportions. And just like chapter 7, we're going to find that reducing our confidence down to 95%, just that little bit of drop in confidence, means we can shrink that interval down quite a bit and really gives us a good idea of what the population mean size is. All right, and last one, if the method has a 10% confidence level, then the method works in 10% of the surveys. This is another one that's probably isn't going to be used very often. And it'll give you a really narrow interval, but it's not going to be very useful because it doesn't work all that often, or it's not successful that often. Okay, we say that the method works if the interval captures the true value of the population parameter. In other words, the interval works if the true population mean is inside the interval. Keep in mind that the population mean does not move. It's always the same. It's fixed. However, the confidence interval does change with every random sample collected. Thus, the confidence level measures the success rate of the method, not of any one particular interval. All right, so how do we choose a level of confidence? Let's take a look at a diagram illustrating 4 different confidence levels for the researcher's sample mean of 9 hours. The X-bar was 9 hours, and the estimated standard error was 0.6 hours. And this is a very similar diagram to what we saw in chapter 7. We're going to look at a confidence level of 68%, which note is just one standard error. It's not a very high confidence level. But note if we go up to 2 standard errors, we have a big jump in confidence, but we're not making the interval too much wider. 3 standard errors, not a big change in our confidence level. We're going to be 99.7% sure or confident, but we still had to go 1 more standard error on either side. This is 3 standard errors. And 4 standard errors, 99.9% confident, or actually 99.99% confident. We go 1 more standard error above and below. So typically we choose this 95%. That's again the most common one, just like chapter 7, because of that increase in confidence without having to widen the interval too much. All right, so some notes here. If we increase the margin of error from 2 standard errors to 3, we gain only a small amount of confidence, from 95% to 99.7%. If we decrease the margin of error from 2 standard errors down to 1, we lose a lot of confidence, and the confidence level falls from 95% to 68%. So 95% is kind of the happy middle, where we've got a lot of confidence, but we didn't have to make the interval too wide to accommodate that. All right, so note this process is similar to the process used in chapter 7. The more confident we want to be in our interval, the more standard errors we have to use or should use. But we're going to be using something called the t-distribution rather than the standard normal distribution to find our multiplier or critical value. So remember in chapter 7, we call these critical values z star. In chapter 9, because it comes from a different distribution, the t-distribution, we're going to call these critical values or multipliers t star. And we do that because of that substitution. Most of the time, we're not going to get the standard error. Instead, we're going to have to use the estimated standard error. There's just a little bit more uncertainty with that substitution using S instead of sigma. In fact, let me write this in a different order because in this one, we use sigma. In this one, we have to use S. And although S is an unbiased estimator of sigma, there's still a little bit of uncertainty in terms of whether they're the same or very close. So it turns out that this multiplier that we're going to use is going to be a little bit bigger. It's going to make up for that uncertainty in this substitution. All right, so on the next page, the formula for a confidence interval is x bar plus or minus that critical value. So notice it's a t instead of a z, times the standard error that's estimated. So we're still taking a couple of standard errors. And that standard error, just like we've seen before, is your sample standard deviation divided by the square root of your sample size. All right, so some notes below about all these symbols, just some reminders. First one, remember that x with the bar on top, or x bar, is your sample mean. Lowercase n is your sample size. T star is your multiplier, and it's chosen to achieve the desired confidence level, sometimes referred to as a critical value, just like chapter 7. And there's a little bit more about this below that we'll get to. SE EST, or standard error estimated, is the estimated standard error. And your margin of error, M, or MOE for short in some situations, is just a couple of standard errors. How many standard errors depends on that critical value and the confidence that you want. And a last reminder here, just like chapter 7 again, you have to check those central limit conditions first. This formula depends on those conditions being met. If you apply that formula and the conditions haven't been met, then you're going to get a confidence interval that can be very misleading. All right, number 9, back to that multiplier, T star. It's a constant that's used to fine-tune the margin of error so that it has the level of confidence you want. We're going to use the T distribution. It's going to have something called degrees of freedom. We're going to use n-1 degrees of freedom to find this multiplier. n-1 is 1 less than the sample size. So take your sample size n and subtract 1 from it, and you get your degrees of freedom. Okay, the degrees of freedom determine the shape of the T distribution. As the degrees of freedom increase, so as your sample size gets bigger, the T distribution gets closer to the standard normal distribution. So we've got 3 different ones here. They're all shown below on the same scale as the standard normal distribution. So I'm going to outline in red the T distribution. Notice it's also symmetrical and mound-shaped. Oops, got a little off track there. But its tails are thicker. So it's a little bit more spread out. And this is for degrees of freedom equal to 1, which means the sample size was 2. Here, if we go up to a sample size of 11, 1 less than that gives us the degrees of freedom of 10. Notice the tails are still a little bit thicker, but it's a lot more similar to the standard normal distribution. And they're getting too close together so much so that I can't really draw it. In fact, when we get up to here, degrees of freedom of 40, which means our sample size was 41, we can't tell them apart anymore. They look fairly similar, at least to the naked eye. Right? So some observations about this T distribution. 1, the T distribution is symmetric, mound-shaped, unimodal, the same characteristics as a normal distribution. 2, the T distribution, though, here's the difference, has thicker tails than the standard normal distribution. And these tails get thinner as the degrees of freedom increase. So remember, degrees of freedom increase means sample size increases. Okay, and then the last thing, those thicker tails indicate that extreme values are more likely. So if you have a really small sample size, let's say 2 people taken out of the population, it's much more likely that you're going to get something unusual there. So those thicker tails accommodate that, and they make our intervals wider to make up for that uncertainty. All right, so why do we use the T distribution rather than the standard normal distribution? It's because we're using an estimated standard error rather than the standard error itself. The estimated standard error uses S, which is your sample standard deviation, in place of sigma, which is your population standard deviation. And although S is an unbiased estimate of sigma, there is the potential that this estimate is not as close as we would like, especially with smaller sample sizes. So if you're dealing with a smaller sample size, S may not be as close to sigma as we want. Maybe put a line through that. And you're not as likely to get extreme values, right, with a smaller sample size. You might think there's less spread. It's also the case where you might get a really unusual value and it inflates the standard deviation. So it might be a lot bigger than you expect. But that uncertainty leads us to use a bigger multiplier. So using the T distribution to get our multiplier makes up for that uncertainty. Right. So in most cases, the critical value from the T distribution is going to be bigger than the one we would have gotten from the standard normal distribution. And that is going to lead to wider intervals. And this is especially true for those smaller sample sizes. All right, so on the next page, you have a copy of the T distribution from the back of your text. We're going to look at the column for the 95% confidence level and see what happens to our critical value, T star, as the degrees of freedom increase. All right, so notice that up here we've got confidence levels in our headings. So we can do 80%, 90%, 95, 98, 99, and 99.8. We're not going to get other confidence levels other than those for the purposes of this table. We're going to focus on this column for now. Okay. So we're going to scroll down, see what happens. And notice that these rows are based on degrees of freedom. So that first entry is for a sample size of 2. 1 less than that gives us degrees of freedom of 1. So as our sample size increases, and our sample size is increasing as we go down through the table, notice that these critical values are getting smaller. In fact, if we go all the way down to the bottom, let's see if I can get that on the screen, you might notice or recognize that last value in the table. Right? If our sample size is infinite, notice that this is the Z-star value that we would have used for a 95% confidence level. You can flip back to chapter 7, press pause, you can double check that, it's there. And that means that as our sample size gets bigger, T-star is getting closer to Z-star. It's getting closer to what we would have used from the standard normal distribution. Right? Also note, let's look at that middle row, or sorry, middle column. Look at how big our critical value would have to be if we use a sample size of 2. And there's a lot of uncertainty with that. So this critical value is going to make our interval pretty wide. Right, a couple of notes, convention. And if you look at degrees of freedom, you'll start to see right about here, there's some jumps. So there's going to be some sample sizes where you don't have a row on this table you can go to. The convention is, let's say you want to use a sample size of 35. Degrees of freedom then are 34. Since 34 is not in the table, we're going to go up a row on the table, and we're going to use 30, the entry for 30, because it gives you bigger critical values than using 40. So it goes with a more conservative or cautious approach, a more wider interval instead of a narrow interval. So, and if you have to, if you don't have an entry in the table that you need, you go up a row on the table. Use a smaller degrees of freedom, which means you're using a bigger critical value. Okay, so let's use this t-distribution to calculate a 99% confidence interval for the researcher sample of 25 iPad batteries. Just a reminder that x bar is 9 and s is 3. So we're going to use the formula x bar plus or minus a critical value times the estimated standard error. So we've got 9 plus or minus. We're going to go back to the table on the previous page. We have, let's see, a degrees of freedom of 24. So we want to use the row for degrees of freedom of 24. And we are doing a 99% confidence level, which is the second to last column in the table. So our critical value is going to be 2.797. And I'm not going to go up on the screen, but if you scroll up on your papers, you'll find that that's underneath the 99% confidence level. All right, so we're going to use 2.797 times 3 over the square root of 25. All right, so we get 9 plus or minus 1.6782. And again, you may want to press pause to verify that. So we can say that our confidence interval is from 7.3218 up to and including 10.6782. Okay. So 99% confidence interval for the mean battery life of all iPads. I'm going to round a little bit here, 7.32 hours up to 10.68 hours. And so finishing up, we're just going to take a quick look or a closer look at the confidence interval we just calculated. So this confidence interval tells us that any value between 7.32 hours and 10.68 hours is a plausible value for the mean battery life of all iPad batteries. So mean battery life of all iPad batteries, remember that's mu. We're saying that mu could be any one of these values. Right? Any value outside this confidence interval is not a plausible value for the mean battery life for all iPad batteries. It's not impossible that the population value is outside this confidence interval, but it would be very surprising. Right, and we can interpret this confidence interval as follows. Notice we're using the word confident. We can be 99% confident that the mean battery life for all iPad batteries is between 7.32 hours and 10.68 hours. And that idea of confidence, again, comes from the idea that this procedure would work 99% of the time. 99% of the time you would get a sample mean close enough to the population mean for this interval to be successful. So that leads us to this part here. If you were to repeat this survey many times, then in 99% of the surveys, the resulting confidence interval would succeed in capturing the mean battery life for all iPad batteries. All right, last up, our confidence, remember, is in the process that produces the confidence interval, not in any one particular interval. It's incorrect to say that a particular confidence interval has a 99% or any other percent chance of including the true population parameter. Instead, we say that the process that produces confidence intervals captures the true population parameter with a 99% probability. Recommendation to you is use the idea or term confidence. Try and stay away from the word chance or probability when you're interpreting these intervals. And you really want to focus on this idea here. This is the best way to interpret these things. That you're 99% or some other percent confident that your mean is in between these two values in your interval. And then last thing I want to point out is you're never going to know for sure with 100% certainty that mu is in this interval. And again, that's another reason why we're using the word confident. We're confident it's in there because we know it happens more often than it doesn't.